Greetings, geometry students. We have a test coming up on Monday, so we're going to spend a little bit of time reviewing. But as I'm sure you already know, there's not a whole lot of information in this unit. There's a few formulas, and the bulk of the unit is going to be based upon your ability to use those formulas, apply them to the correct shapes, work the correct math in order to arrive at the correct answer. Also keep in mind, as with any test, the unit that we are on is not the only information that shows up on the test. So don't think, hey, there's nothing really to study for this unit, because any questions from any unit that we've covered this year are fair game to show up on the test. So please make sure that you do not disregard previous material and just wait until the semester exam. Because if you kind of get to thinking about it, any test that we see is a potential semester exam. They can ask any questions they want from any unit that we've talked about. Anyway, let's take a quick look at the area of triangles and quadrilaterals. The bulk of the information, the bulk of the formulas that we talked about during this unit are in this very first unit, or very first lesson. And it's going to be up to you. I will provide you with the formulas themselves, but I'm not going to label them, go, ooh, here is the formula for the area of a parallelogram, and ooh, here is the area for the formula for the area of a triangle. Okay, I'll provide you with the formulas. It's going to be up to you to decide which formula actually applies for the particular shape that you're looking at. Okay, so you're going to have to know which formula is which. Okay, so we started off with the basic definition. Obviously, area is the amount of stuff required to fill a two-dimensional object. Then we talked about our most basic polygon that we have, which is the three-sided polygon, the triangle. And the area of a triangle is found by multiplying 1/2 times its base times its height. And this was the first instance of the unit where we discussed the fact that a base and a height in geometry do not necessarily have anything to do with being on the bottom or being straight up and down. For the words base and height in geometry mean two of the sides of your polygon that are perpendicular to each other, or not even necessarily two sides of the polygon, but two measurements within the polygon that are perpendicular to each other. Those are base and height. Gave you an example on triangles, and then we got into the parallelograms. Okay, well, the area of a parallelogram is found by multiplying its base times its height, and once again, that does not have anything to do with being on the bottom or straight up and down. Okay, it has to do with two measurements within the polygon that are perpendicular. Okay, we talked about a rhombus. A rhombus is a type of parallelogram, so the formula remains the same, base times height. Rectangle, same, it is a parallelogram. Okay, so its formula is base times height. The difference with a rectangle is that the base and the height are actually sides of the polygon. Okay, it does not happen in all polygons, obviously, but it does in the case of a rectangle. Square is a special kind of a parallelogram. And as we discussed later on in this unit, there's actually a few different formulas that you can use in order to work with a square. Now, it is a parallelogram, so we can absolutely treat it as base times height. The catch with a square is that since the base and the height are congruent to each other, calling one side the base and one side the height almost suggests that there would be a difference in the two. Well, there's not a difference in the two when it comes down to being a square. It's the same measurement twice. So instead of saying base times height, we typically say side times side, which of course simplifies into side squared. And trapezoid, different type of a shape. It only has one set of parallel sides. So the formula you're looking at for this one is actually very similar to the formula for a triangle. 1/2 times the sum of the bases times the height. And actually, if you kind of get to thinking about this, a trapezoid is basically like a triangle that has been split in half or into at least two pieces and has a rectangle jammed into the middle of them. Okay, so you have that 1/2 times base times height idea of a triangle, but we have to consider both bases in there because of the rectangle that fits into it. So, you know, in the idea of the composite shapes that we've talked about here lately, okay, a trapezoid could also be thought of as a triangle on the left side, a rectangle in the middle, and then a triangle on the right side. And that's how come the formula looks very similar to triangle's formula. And then lastly, we talked about the kite. Okay, as I told you before, most textbooks do not even reveal this formula to you. Okay, but it's a good formula, I believe, where the area of a kite is found by multiplying 1/2 times the length of one diagonal times the length of the other diagonal. Now, this formula is a good formula not only because it helps us find the area of a kite, but also because it works for the area of any quadrilateral that has perpendicular diagonals. Okay, and of course the quadrilaterals that have perpendicular diagonals are the kite and also the rhombus, which has another formula, base times height, so we can use either of those. If you have a rhombus where you have base and height, we'll use that formula. If you have a rhombus where you have information about the diagonals, well, then you might want to use this formula. And also another quadrilateral that has perpendicular diagonals is special kind of a rhombus, the square. So we could use the formula side squared if you have information about the sides of a square, or you could use this one, 1/2 times d1 times d2, okay, if you happen to have the information about the diagonals instead. Okay, so you've got some options as far as your formulas are concerned. Okay. And there you go. Now, the last thing we did talk about is this is the textbook way of going about the formula for the area of a kite is to think about the kite as 4 triangles, and then you can apply your formulas for triangles to find them if you want. But in either case, whether you use the idea of a kite being 4 triangles or just treat it as the shape kite, in either case, you're going to have the information about the diagonals. So it seems to me you'd probably want to use the formula that does work with the diagonals. But that's up to you. Okay, after that, we came back and we spent a day looking at more advanced area problems. Now, on this day, we did not reveal any new information or anything like that. On day 1 with the area formulas, we saw that sometimes we're provided with all the information that we need, and all you have to do is get the right formula, plug the numbers in the right places, and you get your answers. Okay, but more realistically, what's going to happen is you'll have to identify your shape, you'll have to select the right formula, you'll have to plug in the numbers in the right place, of course, and you will end up with at least one piece of necessary information that is missing. You'll have to solve for that piece of missing information, which usually involves building a triangle somewhere in your polygon and then applying either the Pythagorean theorem or one of your trig functions, SOHCAHTOA, in order to find your missing side length of your right triangle, and then that becomes the piece of information that you needed to plug into your formula, and then you're good to go. Okay, the next information that we looked at was new, and this deals with the area of the special shapes that we call the regular polygons. Okay, now of course a polygon is said to be regular if it has if it is both equiangular and equilateral. Okay, now there's a little bit of new vocabulary that goes along with regular polygons, some new things inside of the figures that we had not ever looked at before, and that is the idea of a radius applying to a polygon. And a radius simply means the longest distance from the center point of a polygon to its perimeter. So in a regular polygon, that happens from the center point of the polygon out to the vertices, out to the vertex, okay, of the polygon, the corner points. And then we have another new term, which we called the apothem. Apothem means shortest distance. Okay, so we're talking about the shortest distance from the center point out to the perimeter of the polygon. And that shortest distance occurs when you basically extend a line segment from the center point out to the perimeter, and you position it such that it forms a right angle with the side of the polygon that it's connecting to. Now, this becomes a very important concept in a regular polygon, as you can see on those figures in the center of the screen there, is that if you look at an apothem and a radius positioned kind of adjacent to each other, then you can absolutely see a right triangle that's formed in between the apothem and the radius and half of a side length of the regular polygon. And that's important because we said a lot of times our missing information that we need for our area formulas can be discovered by looking at a right triangle or positioning a right triangle connecting to the information that you need. And then you can do Pythagorean theorem or SOHCAHTOA, and you will find your missing information, and you can go from there. Now, special formula for the area of a regular polygon is 1/2 times the apothem times the perimeter. Now, of course, keep in mind, perimeter is pretty easily found for these guys because the regular polygon has all of its side lengths the same measurement. So if you can find any information about any one of the sides, then chances are you can find your perimeter. Okay. So not a whole lot of really special information going on with the formula or anything like that. It's just plugging information in. But we did take a little bit of time to look at a couple of special cases for regular polygons. One of them is being the regular hexagon. This is a figure that is picked on quite frequently when it comes to regular polygons because of what happens when you start to draw in the diagonals of the regular hexagon. So there are 3 diagonals in a regular hexagon. You can see them drawn in at the bottom of the screen there. Now, what starts to happen here is if you take the central angle, okay, inside of the regular hexagon, okay, if you take the central angle and divide that 360 degrees up that it takes to travel all the way around the hexagon one time, divided up by the 6 triangles that are formed inside of there, the angles are all divided equally. So each of those central angles marked at the center of the screen right there, those are all 60-degree angles. Okay. Now, at the bottom of the screen, as you can see, the radii inside of the regular hexagon, okay, obviously from the center point out to each of the vertices, those are going to be congruent. So all 6 of the radii are congruent, so they are given 1 tick mark each. Okay. Now, since in each of these triangles that we now have isosceles triangles. 2 sides are definitely the same because of the radii all being congruent. If 2 sides of the triangle are congruent, then the relationship will be that 2 angles across from those congruent radii will be congruent also. So if you take into account that each of the triangles in the figure already has a 60-degree angle in it, well, that leaves 120 degrees for the other 2 angles, and we just said that those 2 angles are going to have to be congruent, so that 120 degrees is shared equally. That makes each of those 2 angles also 60 degrees. So all 3 of the angles in these 6 triangles are all 60 degrees. So you can see now that they all have the little 1 angle congruency mark on each of them as well. Okay. Well, again, back to the relationship inside of a triangle. If all 3 of your angles are going to be congruent, that means all 3 sides are going to be congruent as well. So the tick marks expand even further, and you end up with all 3 sides in each of the 6 triangles, all having the 1 tick mark. Okay. So the end discussion of all of that is that in a triangle, let me jump back, in all 6 of these triangles, you have 6 regular triangles. Okay, so the kind of the final statement on that is a regular hexagon is built out of 6 regular triangles. Now, if you take one of those triangles out and look at it, or any of those triangles out and actually look at it a little further, if you were to drop an altitude into one of these triangles, like is shown there, okay, since it is an isosceles triangle, this altitude, which forms a right angle with the side of the triangle, okay, also becomes an angle bisector. So the angle at the center of the hexagon is bisected. So instead of 60, it becomes 2 30s. And now what you have is each triangle is subdivided into 2 30, 60, 90 right triangles. Okay. Now going back and remembering your rules or studying your rules for 30, 60, 90, which you might want to do, that means that the hypotenuse of these triangles is going to be twice as big as the short leg, and the long leg of these triangles is going to be whatever the short leg is, times the square root of 3. Okay. Now also keep in mind that this triangle came from the interior of the regular hexagon. So the altitude that we just drew inside of this triangle is actually from the center point of the hexagon directly over to the side. So it's not just an altitude for this triangle, it is an apothem for the hexagon. So you can kind of see how all this stuff is very tightly related, and they have every right in the world to ask you any bit of this information about the hexagon. So if you're going to spend some time studying, getting ready for this test, which would be a good idea, you might want to spend some time making sure that you completely understand the regular hexagon. Another shape that we probably need to be familiar with on a deeper level is our friend the square. Now, we've already talked about the square a good bit. We've already come across now 3 area formulas for it. We got the side squared, we've got the 1/2 times diagonal 1 times diagonal 2, and now we have the regular polygon formula, 1/2 times the apothem times the perimeter. So we have a lot of options as far as finding its area, but then here comes more information. When you start drawing in, again, the diameters for your regular quadrilateral, your square, something starts happening. Okay, the right angles that are in the interior of the square are bisected by the diagonal. That means each square, by drawing in a diameter, you can end up with 2 45, 45, 90 right triangles. And once again, you might want to rediscover the formula for 45, 45, 90s, and that formula is the hypotenuse equals whatever the leg is times the square root of 2. Further, okay, this relationship continues on. If you draw in the other diagonal, then your square is not split into 2 45, 45, 90s. It's actually split into 4 45, 45, 90s. And as you continue to subdivide these triangles by way of installing altitudes inside of them, then your 45, 45, 90s continue to get divided into more and more and more 45, 45, 90s. And as you can imagine, this can get as bad as the person putting the diagram together feels like making it. So please understand the relationship between the square and the 45, 45, 90s that are built inside of it. The rest of this should have been just examples. And then finally, the area of composite shapes. Now, there is nothing really new to understand here. It's just a different methodology for thinking. Okay, we are not looking at figures that we recognize. They are not figures that fit neatly into our little flow charts of quadrilaterals or anything like that. So what you need to do is you need to find a new way of thinking about these shapes so that you can understand them. Okay, so the big block-shaped L at the top of the screen, the concave hexagon would be its proper term. Okay, we don't have a formula for it, but it can be broken down into smaller shapes that we do understand that can then be added together, like you see at the bottom of the screen. Or perhaps another way of thinking about it would be to consider a larger shape that has had a smaller piece of it removed. Okay, but once again, figuring out shapes that we can understand so that we can either add some smaller shapes together with formulas that we do understand, or bigger shapes that have formulas where we can start subtracting smaller shapes that also have formulas away from them. So it's just a matter of engineering your mind to recognize or to consider creatively what you might actually be looking at. Okay, so that's basically the information. The rest of this lesson was just examples. Okay, so it's a finite amount of information that you actually have to know for the upcoming test. Okay, again, I will give you the formulas, but I will not tell you which formula is which. It'll be up to you to recognize it and apply it correctly, and then work on your answer from there. And please do not disregard information from previous units. Just because we're not talking about Unit 7 does not mean they might not ask information about Unit 7. The same would be true for Unit 6 or Unit 2 or Unit 5 or anything like that. Don't just throw it away and forget about it. That's how some of you got killed on your semester exam last semester. Let's not let that happen again. Please review old information. Don't save it until the last minute. Anyway, there's your review. We'll see you at the test.